My name is Christian Kaufmann, and today I want to give a short webinar and an overview of how I used RIPE Atlas in the past and how it helped me to do my master thesis. It is probably fair enough to say that the study is like 3 years old and the dates might have changed and the numbers, but the approach and what you can actually do with RIPE Atlas and how important the tool can be for your research and your study, I think is still valid. I did a master thesis of analyzing the internet connection density between IPv4 and IPv6. What does that mean? Well, how many peerings and interconnects do we actually have in the two protocols? And what does that actually mean for performance and speed, and how does that has changed over time? So, what was the issue? Well, the IPv6 latency, especially in the past, was not the same as IPv4. That had various reasons. MTU, tunnels, hardware, and as I tried to prove, the interconnection density in IPv6 were random reasons for that. I tried to focus on the interconnection density here and not on tunnels, hardware, or any other happy eyeballs or fallback scenarios. What I tried to figure out 3 years ago was how is it actually different and what can we as a community do to potentially improve the connection density in IPv6. So, you can do that in various ways, right? You could, in theory, just count all the different sessions on v4 and v6, and you would get an idea if we have the same and if therefore the interconnection density is the same. Unfortunately, there is no central repository where you can actually ask all the people and try to figure out how many sessions we have. You could look in Lookingglasses or route view servers, but first of all, they wouldn't cover the whole internet, and on the other side, what they actually would give you is just the best path. They wouldn't tell you all the other paths which they haven't chosen, and therefore it is an incomplete view because you look at aggregated data. My approach was to measure the network latency with pings and traceroutes. To get a representative sample, I thought about, I choose 500 sources and 500 destinations, and then I make a 500 by 500 matrix, and I do that for v4 and v6. And then I should have enough data points to have a halfway representative cycle. So what I did is I have chosen RIPE Atlas. And if you look at 500 probes by 500 destinations, you do that for two protocols, v4 and v6. And then you actually measure the round trip times, the IP hops and the ASN hops, you get 1.5 million data points. So you have quite a data sample to actually make a statement where we stand at a given time. One of the features at RIPE Atlas is that you can have a lot of probes, and you actually can even go and set a fixed set of probes. So when you make repetitive studies and you actually look at them again and again, that you use the same probes. This is important, otherwise if you use always random probes, then you can't really compare your study. So I used 500 probes which were connected to v4 and v6, otherwise you can't compare how they are connected to the internet. And then I have chosen 500 destinations. For this I went to the 500 biggest Alexa sites and I kicked all the ones out which were either on CDNs or anycasted, because I wanted that the packets really travel through the internet and not that one probe goes to another destination, even if it's like the same website, it would be a different IP address and therefore not comparable either. I then wrote a Python script which talks to the Atlas API, because you don't want to click 500 probes to 500 destinations in a GUI. And I was running the v4 and v6 trace routes to all these 500 destinations. The results are getting stored in RIPE Atlas in JSON format. And I wrote a script which downloads the 1000 JSON files for v4 and v6 separate. And then the number crunching starts. So this data I used to fetch, first of all, the ASNs for the hops and the trace route. So you take the trace routes, you take the IP addresses, And then you go back, like with the Team Symru IP2 ASN database, and then you see which ASN is actually the packet going through from your probe to the destination in one of the test scenarios. You also get out of the JSON file the round trip time, so you know how long the packet has traveled. And then I created a matrix and showed the differences. So I could compare v4 and v6 round trip times. I was looking into the IP hop count. Is the hop count and actually the path the packet has traveled from the probe to the destinations for both protocols the same? And I also looked at the ASN path. Did they actually go through the same ASNs, or were different ASNs used? The result was quite interesting. So on one side I got a lot of false results where the v6 hop count, for example, or the ASN hop count was just a 1 or a 0. So that seems to be the result of tunnels, where it really the packet travels for most parts through the tunnel and then comes out close to the destination, and you don't really see which underlying infrastructure it has used. But even if you take these ones out of the equation, then what I could see was that IPv6 had a slightly lower ASN hop count than IPv4. And in general, the majority of all ASN hops were between 2 and 6. So there were not many outliers which were either fundamentally longer between the two protocols, and therefore I think quite comparable. Looking at the round trip times, there was not much difference between both protocols. So the round trip diversity didn't show any specific clustering and was widely spread over all probes, depending on where I have chosen them in the first place, right? The probes were selected from all over the world, but then I always used the same ones. The strongest clustering was between 0 and 75 milliseconds, so this was the majority of all round trip times. And then it faded out to 500 milliseconds, but probably more because the destinations were quite far away from the probe than rather that there was a big difference between the two protocols. I then looked at the median of the round trip times, and because that is interesting, right? The round trip time of the packet is always, it depends on how it travels over the infrastructure and the fiber. So it is actually agnostic to the ASN hops or the IP. So even if you have tunnels, it still has to travel from A to B, and therefore it's good to compare the two numbers. The round trip times results showed a little bit more outliers for IPv6, but it had actually less spread. So where it worked and where everything was fine, IPv6 was actually slightly faster in the round trip times, but then you had more outliers which probably just traveled half around the world before they made it to a destination, because of either some strange configuration in the networks or because of a lower interconnection density, so there was just not a peering configured in the same metro area or in the same country, and therefore the packet traveled further till it reached its destination. I looked at 4 scenarios. The first scenario was I looked at the amount of occurrence in percentage. How often is the ASN path and the IP hops exactly the same in v4 and v6? So the assumption is that this is exactly the same path a packet was traveling for both protocols. And that occurrence was actually just 6%. So a very small number, and probably much smaller than I expected at the time. Scenario number 2 was, in which cases do we actually have the same ASN path? So it travels through the same providers, but the IP hops are different. So that means that the networks have the same peering between v4 and v6, but either on different routers or not as often for v6. And therefore it travels through the same networks, but not through the same routers. that actually occurred for 24% of all cases. So roughly a quarter, you use the same providers, but different router in different cities or different path. Scenario number 3 was where both the ASN path and the IP hop path was different. So IP hop makes sense, I guess. ASN path is related to the fact that there was probably a peering missing between two providers, and you traveled through a third-party provider to reach the destination. This was actually the case for 62%, so more than half of all cases traveled different in v4 and in v6 on an ASN path. Scenario number 4 was actually more for entertainment, but still brought a little bit a strange result, and that was where the ASN path is different. So it goes through different providers, but by accident the IP hops are the same. And that occurred for 8% of our cases. So it is actually, 3 years ago, it was more likely that the IP hops are by accident the same amount, even if you travel through different networks, then you actually had exactly the same AS path and the same IP hops. So the result of my master thesis at the time, and I think by now the numbers are probably outdated, is that IPv6 was not much slower than IPv4, if at all, but that the amount of interconnections, so how many peerings we have and how many sessions are in v6 in comparison to v4 was actually quite a bit lower. So I guess the result out of that is if you have large scale tests you want to run between protocols and compare them, RIPE Atlas is a good tool because you can go and fix the probes, so you have the same probes and you can run them against different destinations, so you can repeat the test over time and you can compare it. But it also gives you enough diversity over the planet to really have different test scenarios. And with the API, where you can trigger everything from a script and then download it and number crunch it afterwards, it is really good for large scale. So this is much more powerful than like a Lookingglass or a ping or a traceroute where you have a single destination. With that, you really can measure big parts of the internet for various cases. Thanks a lot.